There's a machine hurtling through absolute darkness right now, 13 billion miles from home, powered by decaying plutonium, sending whispers back to Earth that take 19.5 hours to arrive. Voyager 2 crossed into interstellar space in 2018, but here's what most people get wrong. It hasn't actually left the solar system, not even close. And where it's headed next, the final destination it will reach before going silent forever, is so far beyond anything we typically imagine that the numbers stop making sense. 300 years from now, it will just be arriving. The spacecraft launched from Cape Canaveral on August 20th, 1977, with computers less powerful than your phone and a mission timeline measured in months, not decades. Nearly 50 years later, it's still functioning, still transmitting, still traveling at 34,000 miles per hour through a void so empty it makes the best laboratory vacuum look crowded. Every second, it moves another 9 miles farther from the only planet where anything knows it exists. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Right now, as you're reading this, Voyager 2 sits at a distance of roughly 142.5 astronomical units from Earth. 1 AU is the distance from our planet to the Sun, about 93 million miles. Neptune, the most distant planet in our solar system, orbits at only 30 astronomical units. Voyager 2 has traveled more than 4 times that distance. The spacecraft has been flying for so long that it has covered more ground than the entire span from the Sun to Neptune, then done it 3 more times, and it's still going. But distance gets weird when you're talking about interstellar space. The heliopause, that boundary where the Sun's influence finally yields to the interstellar medium, sits at about 120 astronomical units. Voyager 2 crossed it on November 5th, 2018, becoming only the second human-made object to enter true interstellar space. Its twin, Voyager 1, had made the crossing 6 years earlier, but Voyager 2 had something its sibling didn't: a functioning plasma science instrument that could directly measure the stuff between stars. That crossing felt monumental. Headlines proclaimed we'd left the solar system, except we hadn't. Not technically. The solar system doesn't end at the heliopause. It ends at a place we've never seen, never photographed, never directly observed with any instrument. A vast shell of icy debris called the Oort Cloud, stretching so far into space that even Voyager 2, after traveling for 48 years at speeds that would circle Earth in about an hour, won't reach it for another 3 centuries. Let that timeline sit for a moment. 300 years. Longer than the United States has existed as a nation. Longer than the Industrial Revolution. Longer than the gap between Galileo's telescope and the Wright brothers' first flight. Voyager 2 will drift through the interstellar medium for that entire span before it even begins entering the region that marks the true edge of our solar system's gravitational dominion. The Oort Cloud starts at roughly 1,000 astronomical units and extends outward to perhaps 100,000 astronomical units. Nobody knows for certain because we've never actually seen it. The objects within it are too small, too dark, and too distant for even our most powerful telescopes to detect. We infer its existence from the comets that occasionally plunge into the inner solar system, their orbits traced back to this theoretical shell of primordial ice. Around the year 2326, Voyager 2 will reach the inner edge of this cloud. By then, the spacecraft will have been dead for centuries. Silent, dark, frozen. Its plutonium power source will have decayed beyond usefulness sometime in the 2030s, and its last transmission will have been received by antennas on Earth, operated by people not yet born. The spacecraft will enter the Oort Cloud as a tomb, carrying its golden record of Earth sounds and images into a region of space where the sun appears as just another bright star. And then it will spend 30,000 years crossing it, 30 millennia, just to traverse the Oort Cloud. For perspective, 30,000 years ago, humans were painting caves in France and Spain. We hadn't invented writing. We hadn't built cities. We hadn't domesticated crops or animals. The entire span of recorded human history, from the first Sumerian cuneiform tablets to this moment, fits roughly 6 times into the period Voyager 2 will spend drifting through this cosmic debris field. Despite the Oort Cloud containing billions of objects, Voyager 2 almost certainly won't hit anything. The cloud is unimaginably vast, and the objects within it are separated by millions of miles. The spacecraft could pass within a few 100,000 miles of a comet nucleus and never know it, never be influenced by its gravity, never have any interaction whatsoever. It's like dropping a grain of sand into the Pacific Ocean and expecting it to strike a specific fish. What makes Voyager 2's journey different from every other piece of hardware we've sent into space isn't just the distance or the duration, it's the trajectory. The path it follows through the cosmos for the next millions of years was determined almost 50 years ago by a series of gravity assists from Jupiter, Saturn, Uranus, and Neptune. Each planet bent the spacecraft's path and boosted its velocity without burning a drop of fuel. That final encounter with Neptune in August 1989 set Voyager 2 on its current course. 48 degrees below the plane of the solar system, heading south toward the constellations Sagittarius and Pavo at 15 kilometers per second. This trajectory is essentially permanent. Without propulsion, without any way to adjust its course, the spacecraft will follow this path for geological timescales, influenced only by the subtle gravitational pulls of passing stars and the overall rotation of the galaxy itself. And here's where the story gets strange. Around the year 61,000 CE, Voyager 2 will emerge from the far side of the Oort Cloud, having finally escaped the Sun's gravitational dominance. At that point, for the first time in its existence, the spacecraft will feel the gravitational influence of other stars more strongly than our own. It will have truly left the solar system, but its journey won't end there. It will have barely started. In approximately 40,000 years, Voyager 2 will pass within 1.7 light-years of Ross 248, a red dwarf star in what we currently call the constellation Andromeda. This won't be a close encounter by any meaningful standard. 1.7 light-years is still about 100,000 astronomical units, more than 1,000 times farther than the Heliopause. The spacecraft will glide past this distant star completely unaffected by its gravity, continuing on its eternal trajectory through the Milky Way. Then, around the year 298,000 CE, it will swing within 4 light-years of Sirius, the brightest star in Earth's night sky. 100,000 years after that, it will pass near Delta Pavonis and GJ 754. These aren't destinations, they're just landmarks on an infinite road, stellar signposts marking the passage of epochs. The engineering required to make this possible seems almost impossible when you consider the era in which Voyager 2 was built. The spacecraft's computer has 64 kilobytes of memory. Your phone probably has 1,000,000 times more. The entire system was designed using slide rules and early computers that filled entire rooms. There were no microprocessors, no modern programming languages, no advanced materials, just robust 1970s technology built to last. And it has lasted. 3 radioisotope thermoelectric generators convert heat from decaying plutonium-238 into electricity, providing power through thermocouples with no moving parts. At launch, these RTGs produced 470 watts combined. Today, they generate less than half that, and the output drops by about 4 watts every year as the plutonium decays. This power decline has forced NASA engineers into increasingly difficult decisions about what to keep running. In October 2024, they shut down the Plasma Science Instrument, the very instrument that confirmed Voyager 2's entry into interstellar space. In March 2025, the low-energy charged particle instrument went dark. The cosmic ray subsystem will be turned off in 2026. By the early 2030s, there won't be enough power to run any scientific instruments. The spacecraft might maintain minimal communication capabilities for a short time beyond that, sending back carrier signals with no data attached, just proof that it still exists. Then, one day, it will fall silent. That silence will be permanent. There's no way to reboot Voyager 2, no way to wake it from hibernation, no possibility of recovery. When the power finally drops below the threshold needed to maintain attitude control, the spacecraft will begin tumbling slowly through space, its antenna no longer pointed at Earth, its transmitter broadcasting into the void. But the golden record will remain. Mounted to the side of the spacecraft, protected by an aluminum cover, this 12-inch gold-plated disc contains a message from Earth to whoever might find it. Greetings in 55 languages, music from Bach to Chuck Berry, natural sounds, thunder, wind, whale songs, a mother's first words to her newborn child. 116 images showing mathematical concepts, DNA structure, human anatomy, and scenes from daily life on a planet that will be unimaginably different by the time anyone discovers this artifact. Research suggests the record's exterior face might become unreadable after 5 billion years of impacts from interstellar dust and hydrogen atoms. Voyager 2's trajectory exposes it to less erosion than its twin, giving it better odds. But eventually, the cumulative damage will erase the grooves. The protected side, however, the side facing the spacecraft body, could remain intact for far longer, possibly surviving even the merger between the Milky Way and Andromeda galaxies about 4 billion years from now. The mathematics of that collision are worth considering. When 2 galaxies merge, their stars almost never collide because the distances between them are so vast. But the gravitational chaos can fling stars and planets into entirely new orbits. Some objects get ejected from both galaxies entirely, cast into the intergalactic void. Voyager 2 could be one of them. Imagine the spacecraft, billions of years from now, drifting through the space between galaxies. No stars nearby, no dust, no plasma. Just an emptiness so complete that the density of matter drops to nearly zero. In that environment, erosion would essentially stop. The golden record might remain readable for trillions of years, long after the sun has died, long after Earth has been consumed. long after any conceivable civilization that might have existed on our world has either evolved beyond recognition or vanished entirely. But before any of that, before the distant stellar encounters and galactic mergers, before the incomprehensible timescales of cosmic evolution, Voyager 2 has to survive the next few years of operation. Right now, mission controllers face choices about which remaining instruments to sacrifice next. The magnetometer, the plasma wave subsystem. Each one provides unique data about the interstellar medium, information no other instrument has ever gathered from this region of space. The spacecraft is teaching us things we couldn't learn any other way: the density of interstellar plasma, the strength and direction of the magnetic field between stars, the flux of cosmic rays from distant supernovae. Every data packet that arrives at Earth, transmitted at a rate slower than the earliest dial-up modems, represents knowledge purchased at the cost of nearly 50 years of continuous operation in the harshest environment imaginable. Those transmissions arrive at NASA's Deep Space Network, where 70-meter antennas in California, Spain, and Australia track the spacecraft across the sky. For Voyager 2, the Canberra antenna does most of the work because it's the only dish in the southern hemisphere capable of receiving the spacecraft's incredibly faint signal. 23 watts of transmission power, weaker than a refrigerator light bulb, traveling 13 billion miles through space, arriving at Earth attenuated to a level about a billion times weaker than the power needed to run a digital watch. And yet we can still hear it, still decode the science data, still send commands that take 19.5 hours to arrive, and another 19.5 hours to confirm. The patience required for this kind of communication defies normal human experience. You can't have a conversation with Voyager 2. You can only leave messages and wait almost 2 days for a response. Soon, even that will end. The final command sequence, the last data transmission, then silence spreading outward from the spacecraft like ripples from a stone dropped into a cosmic pond. Except these ripples will never reach any shore. They'll just keep expanding forever, growing weaker and more diffuse, until they're indistinguishable from the background radiation of the universe itself. What happens after that silence falls determines the true nature of Voyager 2's final destination, and why that destination isn't what most people imagine. Because here's what most people misunderstand about Voyager 2's final destination. They think it's a place, a point in space where the spacecraft will eventually arrive, park itself in some cosmic driveway, and just sit there for eternity. That's not how this works. Voyager 2 doesn't have a destination in any meaningful sense. It has a trajectory, an endless fall through space that never stops, never slows, never reaches anywhere final. The spacecraft is falling, and it will keep falling forever through a universe that has no flaw. This distinction matters more than you might think. When the mission controllers at JPL send their final command sequence sometime in the early 2030s, when the last scientific instrument shuts down and the spacecraft can no longer point its antenna toward Earth, Voyager 2 won't stop moving. The silence that follows won't be stillness. It'll be motion without witness, travel without record. The spacecraft will continue on its trajectory at 15 kilometers per second, carrying its golden record into a future where no human might exist to remember what that record means. 300 years from now, around the year 2326, Voyager 2 will reach the inner edge of the Oort Cloud, Not cross some boundary marked by cosmic signposts, but simply enter a region where the density of icy objects increases slightly from nearly nothing to almost nothing. The spacecraft won't notice. There's no instrument aboard that could detect the change even if it were still operating. The Oort Cloud isn't like Saturn's rings, where you can see distinct boundaries and structure. It's a theoretical shell of objects so diffuse that calling it a cloud seems generous. Think about it this way. The Oort Cloud contains billions of comets and icy bodies left over from the solar system's formation. Billions of objects spanning a region that extends from about 1,000 astronomical units to maybe 100,000 astronomical units from the Sun. That's a volume of space so incomprehensibly vast that even with billions of objects scattered throughout it, the average distance between any two objects is measured in millions of kilometers. Voyager 2 could travel through the Oort Cloud for 30,000 years and never come close to seeing anything. The probability of collision is essentially zero, not low. Zero for all practical purposes. You'd have better odds buying a lottery ticket, winning the jackpot, using those winnings to buy more tickets, and winning again, and then doing that entire sequence 10 more times. But here's what makes the Oort Cloud significant, despite Voyager 2 never actually encountering anything there. It represents the true boundary of the solar system. The Heliopause, which Voyager 2 crossed in 2018, marks where the Sun's solar wind gives way to the interstellar medium. Important boundary, historic crossing, unprecedented science. But gravitationally, the Sun's influence extends far beyond that point. Every object in the Oort Cloud orbits the Sun, slowly, over periods that might span millions of years, but they orbit nonetheless. They're bound to our star just as surely as Earth is, even though they're hundreds of thousands of times farther away. The solar system isn't just the planets. It's everything that falls toward the Sun faster than it falls toward anything else. By that measure, Voyager 2 won't leave the solar system until approximately the year 63,326 CE, 61,000 years from now. At that point, for the first time, the spacecraft will feel the gravitational pull of other stars more strongly than the Sun's. It'll still be moving on essentially the same trajectory, still falling at 15 kilometers per second, but now it'll be falling through a gravitational landscape dominated by multiple stars rather than one. The spacecraft will have become, in the most literal sense possible, interstellar, not just traveling through interstellar space, but gravitationally belonging to interstellar space. This is where the concept of destination becomes truly meaningless. Because once Voyager 2 enters the gravitational realm of multiple stars, its path becomes impossible to predict with any precision. Orbital mechanics in a two-body system, spacecraft and Sun, can be calculated with extraordinary accuracy across millions of years. Add a third gravitational source, and the mathematics becomes vastly more complex. Add hundreds of nearby stars, each pulling on the spacecraft with varying strength as their relative positions constantly shift, and you're in the realm of chaos theory. Small differences in initial conditions lead to wildly divergent outcomes over time. We know Voyager 2 will pass within about 1.7 light-years of a red dwarf star called Ross 248 in roughly 40,000 years. We can calculate that encounter with reasonable confidence because it's close enough in time that the uncertainties haven't compounded too severely yet. Ross 248 is heading in our general direction through space, and Voyager 2 is heading in its general direction, and the math says they'll have a distant encounter around the year 41,977 CE, but that about 1.7 light-years contains more uncertainty than you might think. A light-year is 6 trillion miles. Being off by 10% means an error of 600 billion miles. And we're definitely dealing with uncertainties larger than 10% when projecting 40,000 years into the future. After Ross 248, the projections get fuzzier. Voyager 2 should pass within about 4 light-years of Sirius in roughly 300,000 years. Should. Probably. The gravitational influence of every star it passes, every molecular cloud it traverses, every close approach to a rogue planet ejected from some distant solar system, all of these interactions will nudge the spacecraft's trajectory in ways that compound over time. By 1 million years from now, we have only the vaguest idea where Voyager 2 will be. Somewhere in the galaxy, still orbiting the galactic center along with all the other stars, but precisely where? The uncertainty becomes larger than the distance between stars. This is what makes the question of Voyager 2's final destination so philosophically strange. It doesn't have one. It can't have one. The spacecraft will never arrive anywhere. It'll just keep moving through an ever-changing gravitational landscape, its path constantly modified by forces acting on timescales that make human history look like a camera flash. The spacecraft will spend the next 5 to 6 million years crossing what's called the local bubble, a region of low-density gas about 300 light-years across. This bubble was carved out by supernova explosions millions of years ago, massive stars that died in such violent explosions that they swept away the normal interstellar medium and created a cavity of hot, thin gas. Voyager 2 is traveling through a bubble blown by dead stars. When it exits the local bubble millions of years from now, it'll enter denser regions of the galaxy, molecular clouds, star-forming regions, areas where the interstellar medium is thick enough that drag forces could actually slow the spacecraft down over millions of years. Not much, maybe a few meters per second, but enough that the trajectory becomes even harder to predict. And all of this assumes the galaxy itself remains relatively stable. It won't. In about 4 to 5 billion years, the Milky Way will collide with the Andromeda galaxy. Not a collision in the sense of things smashing together. Galaxies are mostly empty space, remember, but a gravitational merger that will completely reorganize the structure of both galaxies over hundreds of millions of years. Stars will be flung into new orbits. Some will be ejected from the merged galaxy entirely, cast into the intergalactic void. Voyager 2 could be one of them. Computer simulations of galaxy mergers show that a small percentage of stars, maybe 1 to 2%, get ejected during these events. They acquire enough velocity during close gravitational encounters with other stars that they escape the merged galaxy entirely. If Voyager 2 happens to pass near a star during the right phase of the merger, it could get the same treatment. Imagine the spacecraft billions of years from now drifting through intergalactic space. No nearby stars, no dust, no plasma, just the cosmic microwave background radiation and the incredibly faint light from distant galaxies. The density of matter in intergalactic space is so low that it makes the already sparse interstellar medium look crowded by comparison. In that environment, erosion of the golden record would essentially stop. The spacecraft would be traversing a vacuum so perfect that collisions with atoms might happen once every few years instead of millions of times per second. The record could remain readable for trillions of years, long after the Sun has exhausted its hydrogen and swelled into a red giant, long after Earth has been consumed, long after any conceivable civilization that might have existed on our world has either evolved beyond recognition or vanished entirely. But this is just one possibility among many. The spacecraft might not get ejected. It might remain part of the merged Milky Way-Andromeda galaxy, continuing to orbit the new galactic center for trillions of years. It might eventually spiral inward through a process called dynamical friction, where gravitational interactions with passing stars gradually rob it of orbital energy. Or it might spiral outward, gaining energy from those same interactions until it reaches the galaxy's outer halo. The truth is, we don't know, can't know. The timescales involved are so vast and the variables so numerous that making predictions becomes an exercise in speculation rather than calculation. What we do know is this: barring some extraordinarily unlikely collision with another object, Voyager 2 will exist for billions of years. The spacecraft itself, the physical structure, will survive essentially intact because there's nothing in space to corrode it or break it down. No oxygen to oxidize the metals, no water to cause rust, no biological processes to degrade the materials, just temperature variations and the occasional impact from microscopic particles. The golden record will erode slowly on its exterior-facing side. Studies suggest that after 5 billion years of travel, there's about a 20% chance that side will be rendered unreadable by accumulated damage from interstellar dust impacts. That's actually remarkably good odds, considering the timescales involved. The spacecraft-facing side, protected by Voyager 2's body, could remain readable far longer. So there's a real possibility that billions of years from now, this 12-inch gold-plated copper disc will still contain readable information about a world that no longer exists. Images of human beings encoded in analog form. Sounds from a planet that was consumed by its own star billions of years earlier. Music composed by civilizations that rose and fell while the spacecraft was still within the Oort Cloud. The final destination of Voyager 2 isn't a place. It's a state, a condition of eternal motion through space, carrying information from Earth's past into a future where that past might be the only record that humanity ever existed at all. The spacecraft will keep falling through the galaxy, through the merged galaxy, possibly through intergalactic space, for timescales that make the age of the universe so far seem brief. And here's the part that should make you pause. That trajectory was set almost 50 years ago by engineers who understood exactly what they were doing. The gravity assists from Jupiter, Saturn, Uranus, and Neptune weren't just about getting better images of those planets. They were about giving Voyager 2 enough velocity to escape the solar system entirely, to become humanity's first intentional messenger to the galaxy at large. Those engineers knew the spacecraft would eventually fall silent. They knew it would drift through space long after everyone involved in the mission had died. They built it anyway and sent it on a journey that will outlast every human civilization that might ever exist. That decision was made with full knowledge of what it meant. The spacecraft wouldn't just explore the outer planets and then quietly drift away. It would become something else entirely. An ambassador, a time capsule, a message in a bottle thrown into an ocean so vast that the bottle might float for longer than stars live. But there's something about that decision that most people miss. Something that reveals just how deeply the Voyager team understood what they were creating. They didn't just build a spacecraft. They built an artifact designed to outlast everything we know. Every component, every material choice, every redundant system was selected not just for the primary mission, but for what would come after. The Golden Record wasn't an afterthought. It was integral to the design philosophy from the beginning. This spacecraft was meant to endure, and endure it has. Right now, while you're reading this, Voyager 2 is approximately 21 billion kilometers from Earth. The number is so large it becomes meaningless without context. So here's context. Light, traveling at 300,000 kilometers per second, takes 19.5 hours to cross that distance. When mission controllers send a command to Voyager 2, they have to wait 39 hours for confirmation that it worked. 19 hours for the signal to arrive. 19 hours for the response to come back. Think about what that means for troubleshooting. If something goes wrong, you can't just fix it. You have to predict what might go wrong, send corrective commands, and then wait almost 2 full days to find out if your solution worked. Every decision becomes a chess game played across billions of kilometers of empty space. The engineers managing Voyager 2 have gotten very good at this game. They've had to be, because the spacecraft is failing, not catastrophically, not suddenly, but gradually, inevitably, the way everything fails when you push it far beyond its design limits. The power situation tells the story most clearly. Voyager 2 launched with 3 radioisotope thermoelectric generators, producing a combined 470 watts of electricity. These aren't solar panels. They're nuclear batteries that convert heat from decaying plutonium-238 into electrical current. Simple, reliable, no moving parts. But plutonium-238 has a half-life of 87.7 years. Every year, the power output drops by about 4 watts. It's been nearly 50 years since launch. Do the math, and you realize Voyager 2 is running on roughly 270 watts now. Less than 3 standard light bulbs. That doesn't sound like much, and it isn't. Which is why mission managers have spent the last decade making impossible choices about what to keep running and what to shut down. The Plasma Science Instrument went dark in October 2024. This was the instrument that definitively confirmed Voyager 2 had crossed into interstellar space back in 2018. It measured the solar wind dropping to essentially zero as the spacecraft left the heliosphere. That data was irreplaceable. Voyager 1's Plasma Science Instrument had failed decades earlier, making Voyager 2's the only functioning probe of its kind in interstellar space. But it consumed power, and power is life. So it was shut down. 3 months ago, the low-energy charged particle instrument was turned off. This device measured particles with energies between 0.5 and 4,000 electron volts. It had been operating continuously since launch, tracking how particle populations changed as the spacecraft moved from the inner solar system through the outer planets and finally into interstellar space. 47 years of continuous data collection, then silence. Later this year, the cosmic ray subsystem will be shut down. That leaves 3 instruments still functioning. The magnetometer, which measures magnetic fields. The plasma wave subsystem, which detects oscillations in the surrounding plasma. And for a little while longer, the cosmic ray instrument that's scheduled for shutdown by the early 2030s, maybe 2032 or 2033, there won't be enough power to run any scientific instruments at all. The spacecraft might maintain minimal communication for a short time after that, a carrier signal with no data attached, just a tone that says, "I'm still here," transmitted across the void. And then that too will stop. Not because the transmitter failed, not because something broke, simply because there's no power left to run it. The RTGs will still be generating heat. They'll keep doing that for centuries, but not enough heat to produce the electricity needed for the transmitter. When that happens, Voyager 2 will go silent. Permanently. That moment is coming. It's not a possibility, it's a certainty. Somewhere between 2032 and 2036, depending on how efficiently the mission team can manage the remaining power, Voyager 2 will send its final transmission to Earth, and then it will become what it was always destined to be: a ghost ship sailing through interstellar space, an artifact from a species that briefly achieved spaceflight and then, as far as the spacecraft will ever know, vanished. The silence won't change anything about Voyager 2's trajectory. It'll keep moving at 15 kilometers per second relative to the Sun. That velocity was imparted decades ago by the gravity assists from Jupiter, Saturn, Uranus, and Neptune. Newton's first law guarantees it'll maintain that speed essentially forever because there's nothing in space to slow it down. No air resistance, no friction, just the occasional gravitational tug from distant stars that might alter its path by tiny amounts over millions of years. So where exactly is it going in this silent future? The trajectory is well established. Voyager 2 is heading south, below the plane of the solar system, toward the constellations Sagittarius and Pavo. Not that constellations mean anything from the spacecraft's perspective. Those are patterns we see from Earth. From Voyager 2's viewpoint, the stars are already beginning to shift position relative to each other. In 10,000 years, the familiar constellations will be completely unrecognizable. But there's a specific star that represents Voyager 2's first close encounter: Ross 248, a red dwarf located in what we currently call the constellation Andromeda. Small star, dim star. You can't see it without a telescope. It's only about 10% the mass of our Sun, and produces maybe 2/1000ths of the Sun's light output. In approximately 40,000 years, Voyager 2 will pass within 1.7 light-years of Ross 248. That's the closest approach to another star system for the next 100,000 years. Close is relative here. 1.7 light-years is still about 10 trillion kilometers. The spacecraft won't be captured by Ross 248's gravity, won't enter orbit, won't even notice the star exists, except as a gradually changing point of light against the background of more distant stars. But it's a milestone. The moment when Voyager 2 becomes closer to another star than to the Sun that launched it. The moment when it truly becomes interstellar rather than just traveling through interstellar space. By that time, 40,000 years from now, what will Earth be like? Impossible to say. 40,000 years ago, humans were still living in small tribal groups. We hadn't invented agriculture yet. Writing was 35,000 years in the future. The pyramids wouldn't be built for another 36,000 years. Everything we call civilization has happened in less time than it'll take Voyager 2 to reach Ross 2 4:8. Every city ever built, every book ever written, every war ever fought, every discovery ever made. All of it fits into a span of time shorter than the spacecraft's journey to its first stellar encounter. And Ross 248 is just the beginning. After passing that red dwarf, Voyager 2 will continue into the deeper galaxy. In approximately 298,000 years, it'll swing within 4 light-years of Sirius, the brightest star in Earth's night sky. The dog star that ancient civilizations worshipped and modern astronomers study intensely. Sirius is actually a binary system. The primary star is about twice the mass of the Sun. The companion is a white dwarf, the collapsed core of a star that exhausted its fuel millions of years ago. Voyager 2 will pass them both at a distance, continuing on its path through the Orion spur of the Milky Way galaxy. Another 100,000 years after that, around 400,000 years from now, the spacecraft will encounter 2 more stars, Delta Pavonis and GJ 754, both relatively close encounters by the standards of interstellar space, both completely meaningless in terms of the spacecraft's trajectory. It'll just keep going. None of these stellar encounters will capture Voyager 2. The spacecraft's velocity is too high and the encounters too distant. It would need to pass within a few billion kilometers of a star, preferably a massive one, to be gravitationally captured. The odds of that happening are vanishingly small, so Voyager 2 will remain a wanderer, passing through the spaces between stars, crossing invisible boundaries between stellar neighborhoods, moving through regions where the Sun is no longer even a particularly bright star in the sky. 5.7 million years from now, the spacecraft will exit something called the local bubble. This is a region of relatively empty space about 300 light-years across, created by supernova explosions that occurred millions of years ago. Those explosions blew away the normal interstellar gas, leaving behind a cavity of hot, thin material. Our solar system happens to be located inside this bubble. So is every star you can see with the naked eye. When Voyager 2 leaves the local bubble, it'll enter denser regions of the galaxy, places where molecular clouds drift between the stars, where dust accumulates, where the interstellar medium is thousands of times denser than the near-perfect vacuum inside the bubble. This could actually affect the spacecraft, not immediately, not dramatically, but over millions of years, sailing through these denser regions could gradually slow Voyager 2 down. Friction is the wrong word, because there's no air, no fluid. But there are collisions, hydrogen atoms, dust grains. Each impact transfers a tiny amount of momentum. Individual impacts mean nothing, but billions of impacts over millions of years might measurably reduce the spacecraft's velocity. Might. The uncertainty here is real. We don't have precise maps of where these molecular clouds will be millions of years from now. We don't know their exact densities. We can't predict how they'll interact with the spacecraft's trajectory. What we do know is that Voyager 2 will keep moving. Whether it slows slightly or maintains its current speed almost exactly doesn't change the fundamental reality. This spacecraft is committed to a journey measured in millions of years at minimum, more likely billions. And somewhere in that distant future, something remarkable could happen. The Milky Way-Andromeda merger. 4 to 5 billion years from now, our galaxy will collide with Andromeda. Not a collision like cars crashing. Galaxies don't work that way. When 2 galaxies merge, their stars almost never actually hit each other. The distances between stars are too vast. What happens instead is a gravitational dance. Stars from both galaxies get redistributed. Some get flung into new orbits. Some get ejected entirely into intergalactic space. Voyager 2 will be there for it. By the time this merger happens, the spacecraft will have been traveling for over 4 billion years. It'll have circled the galactic center roughly 18 times. It'll have passed through multiple spiral arms, through regions where new stars are forming and regions where ancient stars have long since died, through molecular clouds and voids, through neighborhoods we can't even predict because galactic dynamics are chaotic over such timescales. When the merger begins, Voyager 2's orbit around the galactic center will become unstable. The combined gravitational field of the merging galaxies will scramble the trajectories of billions of stars, and one tiny spacecraft along with them. Some computer simulations suggest Voyager 2 has about a 50% chance of being ejected from the merged galaxy entirely during this cosmic reshuffling. 50%. A coin flip across 4 billion years. If it gets ejected, the spacecraft will find itself in intergalactic space, the void between galaxies. Andromeda is currently about 2.5 million light-years away. The nearest galaxy beyond that, Triangulum, is another million light-years further. If Voyager 2 gets thrown into that emptiness, it'll be traveling through the most perfect vacuum that exists anywhere. The density of matter in intergalactic space is roughly 1 atom per cubic meter. Compare that to interstellar space, which has thousands of atoms per cubic meter. The spacecraft would drift for billions of years without encountering anything substantial. But if it doesn't get ejected, if it remains bound to the merged galaxy, it'll continue orbiting. The new galaxy, sometimes called Milky-Way, will be elliptical rather than spiral. Our sun will probably still exist at that point, though it'll be a red giant nearing the end of its life. Earth might still be orbiting, though it'll be a charred rock, long since sterilized by the sun's expansion. Humanity will either be extinct, evolved beyond recognition, or spread across the galaxy in forms we can't imagine. Either way, Voyager 2 will keep going. There's another possibility worth considering: rogue planets. These are worlds that have been ejected from their star systems, wandering the galaxy alone. Recent observations suggest there might be billions of them, maybe more rogue planets than stars. They're incredibly hard to detect because they don't emit light and they don't orbit anything bright. They're just out there, drifting. Voyager 2 could encounter one. The probability is low. Space is vast, and even billions of rogue planets are spread across an enormous volume. But over billions of years, low probability events start to add up. If the spacecraft passed close enough to a rogue planet, within a few million kilometers, the planet's gravity could alter Voyager's trajectory significantly. A Jupiter-sized rogue could completely change the spacecraft's velocity and direction. It could send Voyager 2 into a different part of the galaxy, or out of the galaxy, or, in an astronomically unlikely scenario, into orbit around the rogue planet itself. Imagine that. Voyager 2, billions of years in the future, captured by a wandering world, orbiting a planet that orbits nothing. The golden record preserved in permanent night, circling a frozen world that will never see a sunrise because there's no sun to rise. The timescales we're discussing now are comparable to the age of the Earth itself. Our planet is about 4.5 billion years old. In another 4 to 5 billion years, when the Milky Way-Andromeda merger happens, Earth will have existed for roughly 10 billion years total. The entire history of life on Earth, from the first single-celled organisms to whatever comes after humanity, will be ancient history. Fossils buried in rock layers that might not even exist anymore because plate tectonics will have recycled the crust dozens of times over. Voyager 2 will still be flying. There's something deeply strange about this. The spacecraft was built by a civilization that has existed for maybe 10,000 years in any organized form. Modern industrial civilization is barely 3 centuries old. The space age is less than 70 years old. And yet this machine, built in the 1970s with technology that's now laughably primitive, will outlast everything we know. It'll outlast our species, our planet as a habitable world, our sun as a main sequence star, possibly even our galaxy in its current form. The spacecraft carries no life, no ability to reproduce or repair itself, no consciousness or awareness. It's just metal and silicon and plutonium, following the laws of physics. And yet it'll persist longer than almost anything biological could ever hope to. There's a lesson in that, though I'm not sure what it is. Maybe just that the universe doesn't care about complexity or intention. Simple things, built well enough, can endure. But we're not done yet. Because billions of years is just the beginning. 10 billion years from now, the sun will be dead. Not just dormant or changed, but actually dead. It'll have exhausted all its fuel, swelled into a red giant, then collapsed into a white dwarf. That white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark ember of what was once our star. The planets, if any remain, will be frozen and lifeless. The solar system will be a graveyard. Voyager 2 will have been gone for so long that its connection to that system will be purely historical. It won't be the sun's spacecraft anymore. It'll just be another object in the galaxy, or beyond it. 20 billion years from now, most of the stars in the galaxy will have died. Star formation will have slowed dramatically because most of the available hydrogen will have been used up. The galaxy will be dim, populated mostly by red dwarfs, white dwarfs, neutron stars, and black holes. The era of bright, massive stars will be over. The universe will be entering what's called the degenerate era. Voyager 2 will still be out there. 100 billion years from now, the universe will look completely different. The expansion of space will have carried distant galaxy clusters beyond the cosmic horizon. The Hubble volume, the region of space we can theoretically observe, will contain only the local group, the merged remnant of the Milky Way, Andromeda, and a few smaller galaxies. Everything else will have receded beyond reach, carried away by dark energy. An observer in that distant future would look at the sky and see almost nothing. A few dim stars, darkness everywhere else. They'd have no way to know that billions of other galaxies had once been visible. Voyager 2 will still be moving. Probably. Unless it's collided with something by then, which is possible but unlikely. 1 trillion years from now, the last stars will be dying. Red dwarfs, the smallest and longest-lived stars, can burn for trillions of years. But even they run out eventually. When the last red dwarf exhausts its fuel and fades, the stelliferous era, the age of stars, will end. The universe will enter the black hole era. The only significant sources of energy will be the occasional matter falling into black holes, releasing radiation as it's torn apart. The spacecraft will be unimaginably old by then. Its structure will have been bombarded by cosmic rays for 1 trillion years. High-energy particles striking the hull constantly, displacing atoms, creating microscopic damage. The damage accumulates slowly, but over 1 trillion years, slowly adds up to significantly. Parts of the spacecraft might be noticeably eroded. The golden record's exposed surface will almost certainly be degraded beyond recognition. The protected side might still be intact, but the odds decrease with every passing eon. But the spacecraft itself will probably still exist as a coherent object. It's not going to just evaporate. Solid matter is stable on these timescales. 1 quadrillion years from now, even black holes will be starting to evaporate. Hawking radiation, the quantum mechanical process by which black holes lose mass, is incredibly slow for stellar mass black holes. A black hole with the mass of the Sun would take about 10 to the 67th years to evaporate completely. Supermassive black holes take even longer. But over quadrillions of years, the smallest black holes will begin to fade. Voyager 2 will be... we don't really know. The spacecraft might still be intact. It might have been destroyed by a collision with something, though the probability is still low. It might be inside a black hole, though again, unlikely. Most probably, it's still out there, drifting through the increasingly empty universe. 10 to the 100 years from now, a Google years, all black holes will have evaporated. The universe will enter the dark era. No stars, no galaxies, no black holes. Just elementary particles and photons stretched to impossibly long wavelengths by the expansion of space. The temperature of the universe will be unimaginably close to absolute zero. Nothing will happen. No structure, no complexity, no change except the slow drift of particles away from each other. And Voyager 2, it'll probably still be there. Just atoms now, dispersed across space. The spacecraft won't be a recognizable object anymore. The golden record will have long since eroded away, but the individual atoms that once made up Voyager 2 will still exist. They'll be scattered across light years, maybe more, drifting through the void. Gold atoms from the record, aluminum from the structure, plutonium, long since decayed into lead and other elements. All of it still there, somewhere in the cosmic dark. Protons themselves might decay eventually. The current experimental limit suggests protons last at least 10 to the 34 years. But some theories predict they'll eventually fall apart into lighter particles. If that happens, even the atoms that once formed Voyager 2 will cease to exist in any meaningful sense. The spacecraft will be gone. Truly gone. Not just destroyed or eroded, but decomposed into radiation and exotic particles that bear no resemblance to the machine NASA built in 1977. But we're talking about timescales that make a Google years look short. 10 to the 140 years. Numbers so large they're essentially meaningless. The universe might not even last that long. Depending on the nature of dark energy, space itself might tear apart in the Big Rip, or collapse in the Big Crunch, or undergo vacuum decay that restructures the laws of physics entirely. Nobody knows. We're speculating about events so far in the future that we can barely define the terms we're using. What we do know is this: Voyager 2, built by humans in the 1970s, will outlast almost everything. It'll outlast us, our descendants, if we have any, our sun, our galaxy in its current form, the era of stars, possibly even matter itself, depending on how physics works at the deepest level. That tiny spacecraft, no bigger than a car, represents something extraordinary. It's not just a scientific instrument, it's a monument, an artifact, a message that says we were here, we wondered about the universe, and we built something that would keep going long after we were gone. And that's the weight of it. Voyager 2 carries more than metal and circuits. It carries us. The golden record aboard the spacecraft isn't just decoration. It's a 12-inch disc, gold-plated copper, containing a carefully curated selection of human existence. Sounds, images, music, greetings in 55 languages, natural sounds like thunder, wind, surf, birds, music ranging from Bach to Chuck Berry, from Javanese gamelan to Peruvian panpipes, 116 images encoded in analog form, mathematical definitions, the solar system, DNA structure, human anatomy, scenes of human life, a woman nursing a baby, children learning, people eating, dancing, building, landscapes, architecture, animals. The record's cover includes instructions for playing it, diagrams showing how to decode the images and audio, a map indicating Earth's location relative to 14 pulsars, a sample of the record's audio waveform etched directly onto the surface, all of it protected by an aluminum cover and the gold plating itself. The people who assembled this record in 1977 knew the odds. They knew the probability of anyone finding Voyager 2 was essentially zero, but they built it anyway. Because what else could they do? The spacecraft was going to be out there for billions of years. Might as well say something. Carl Sagan led the committee that selected the record's contents. They had about 6 weeks to choose what humanity should say to the cosmos. Think about that. 6 weeks to summarize our entire species. They argued about what to include, what music, what languages, what images. Some wanted to include images of war, poverty, disease, show the full range of human experience, good and bad. Others argued against it. Why advertise our problems to the universe? In the end, they compromised. The record shows mostly positive aspects of humanity. Our art, our science, our diversity, our children. The message is optimistic, hopeful. But here's the thing nobody talks about. The record was also a message to ourselves. Humanity in 1977 was still dealing with the Cold War. Nuclear annihilation felt possible, even likely. The record was a way of saying, this is who we are at our best. This is what we could be. The golden record will outlast us. That's almost certain. It'll outlast our civilization, our species, possibly our sun. And it's just sitting there on Voyager 2, spinning through the void, waiting for nobody. The exterior-facing side of the record will gradually erode. Studies suggest Voyager 2's record has about an 80% chance of remaining readable after 5 billion years. Voyager 1's record, traveling through a different part of the galaxy, has only about a 1% chance. The difference comes down to trajectory, how much interstellar dust each spacecraft encounters, tiny particles, hydrogen atoms, moving at high relative velocities. Over billions of years, they'll sandblast the record's surface, like wind erosion, but slower, much slower. The protected side, facing the spacecraft body, should last longer. Maybe until the Milky Way collides with Andromeda in 4 to 5 billion years. Maybe longer if Voyager 2 gets ejected into intergalactic space during that merger. But eventually, even the protected side will erode. The gold plating will thin. The grooves will smooth out. the information will fade, unless someone finds it first. That's the gamble. The record exists on the off chance that some other intelligence, somewhere, sometime, might encounter this tiny object drifting through their stellar neighborhood. They'd see it's artificial, they'd figure out it's a message, they'd decode it, and they'd hear Chuck Berry singing, "Johnny B. Gooder." The probability of this happening is vanishingly small. Space is incomprehensibly vast. Voyager 2 is incomprehensibly tiny. The odds of anyone stumbling across it are worse than finding a specific grain of sand on every beach on Earth combined. But it's not zero. And that's the point. The spacecraft itself tells a story too. Even without the golden record, Voyager 2 is recognizably artificial. The geometry, the materials, the radioactive decay products from the plutonium power source. Any sufficiently advanced civilization would look at Voyager 2 and know immediately it was built by someone. They might be able to figure out where it came from. The pulsar map on the record's cover gives Earth's location. Even if the record is unreadable, the spacecraft's trajectory could be traced backward. Follow it back 40,000 years and you'd find Ross 248. Keep going and eventually you'd reach our solar system. They'd know we sent something out into the dark. They'd know we wondered if anyone else was out there. Whether they'd care is another question entirely. But here's what gets me. The golden record represents something deeper than just a message to aliens. It's a snapshot of humanity at a specific moment in time. The music on the record includes Blind Willie Johnson's "Dark Was the Night, Cold Was the Ground," a blues song from 1927. Johnson was a street musician who died in poverty. He never imagined his music would leave the solar system. And yet there it is, on Voyager 2, potentially outlasting every empire, every nation, every city that existed when he recorded it. The greetings include Sumerian, a dead language that nobody had spoken for thousands of years, even in 1977. It's on the record because it was one of the first written languages. A way of saying, this is where human written communication began. The sounds include a mother's kiss, a heartbeat, footsteps, laughter, things so mundane we barely notice them. But they're on Voyager 2 now, preserved in gold, moving through the galaxy at 15 kilometers per second. The images include one of a fetus, human life at its beginning, and another of an old woman, life at its end. The full span of an individual human existence, from conception to old age, encoded on a disc the size of a dinner plate. There's a photo of children learning, a classroom somewhere. Those kids are in their 50s or 60s now, assuming they're still alive. They have no idea they're on Voyager 2. Nobody asked their permission. They're just there, frozen in time, drifting toward the constellation Parvo. The record contains no images of war, no pictures of weapons, no recordings of violence. This was a deliberate choice. Show humanity at peace. Show what we could be, not what we often are. Some criticize this as dishonest, presenting a sanitized version of humanity, hiding our violence, our tribalism, our capacity for destruction. Others argued it was aspirational. This is the version of ourselves we want to present to the universe, our best face forward. Either way, it's what's out there now. The decision is made. The record is 21 billion kilometers from Earth and moving farther every second. The technology used to create the record is almost quaint now. Analog encoding, physical grooves, a stylus-based playback system. In 1977, this was cutting edge. Now it's obsolete. But that obsolescence might actually help. Any civilization advanced enough to travel between stars would probably find analog technology easier to decode than digital. There's a physical relationship between the groove and the sound. No compression algorithms, no file formats, just direct encoding of waveforms. The instructions on the record's cover use mathematical and scientific symbols that should be universal. The hydrogen atom, binary numbers, the speed of light, concepts that any technological species would understand. Whether those instructions will still be comprehensible billions of years from now is debatable. Physics doesn't change, but notation does. The symbols we use to represent concepts might be completely arbitrary. An alien civilization might use entirely different mathematical frameworks. Still, they tried. That's the important part. The people who designed the golden record knew all these problems. They knew the odds were against anyone ever finding it. They knew even if someone did find it, they might not be able to decode it. They knew the record itself would eventually erode away. They built it anyway, because the alternative was sending Voyager 2 into the cosmos with nothing. Just a machine. No context. No message. No indication that the beings who built it had wondered about anything beyond their own survival. The golden record says, "We were here. We thought about the universe. We created beauty. We wanted to communicate." That message will outlast almost everything else we've ever built. The pyramids will erode. The Great Wall will crumble. Cities will fall. Languages will die. Entire civilizations will rise and fall and be forgotten. But Voyager 2 will still be out there, still carrying that gold-plated disc, still broadcasting silence into the void. The last time humans will directly affect Voyager 2's trajectory was in 1989, the Neptune flyby. After that, the spacecraft has been on its own. We can send commands. We can turn instruments on and off. But we can't change where it's going. In a few years, we won't even be able to communicate with it. The power will run out. The transmitters will go silent. The last command will be sent, probably sometime in the early 2030s. And then nothing. Voyager 2 will become an artifact, a relic of the late 20th century, drifting through space with no connection to its creators. The engineers who built Voyager 2 are mostly retired now. Some have died. The scientists who analyzed data from Jupiter, Saturn, Uranus, Neptune are in their 70s and 80s. The next generation of scientists has taken over, but even they'll eventually retire. And eventually, nobody alive will remember when Voyager 2 was operational. It'll become history, then ancient history, then myth, and then, if humanity survives long enough, it might be forgotten entirely. Just another old spacecraft that we sent out decades ago, but it'll still be there, in the year 100,000, in the year 1 million, in the year 10 million, still moving, still carrying the golden record, still representing a moment in 1977 when humanity looked up at the stars and decided to send a piece of itself into the endless dark. That's the real destination, not any particular star, not any specific location. The destination is time itself. Voyager 2 is traveling into the deep future, carrying a message from a species that might not exist anymore by the time anyone finds it. And here's the strangest part, the most profound part, the part that makes this whole mission something more than just exploration. Voyager 2 forces us to think about deep time, about scales beyond human comprehension, about the fact that we're temporary, but our actions might not be. We're used to thinking about legacy in terms of generations. What we leave for our children, our grandchildren. Maybe a few centuries if we're being ambitious. Voyager 2 operates on a different scale entirely. It'll outlast our species, our sun, possibly even the atoms that make up our bodies. And that changes something about how we see ourselves. We're not just living in the present anymore. We're participating in a story that stretches across billions of years. We're part of something larger than nations, larger than civilizations, larger than species. We're part of the universe understanding itself, and that changes how we think about our own existence. Because if Voyager 2 will still be drifting through space long after we're gone, then what we do right now takes on a different weight. Every choice, every creation, every message we send into the future. The engineers who built Voyager 2 understood this on some level. They weren't just building a spacecraft, they were building a monument, a time capsule, a message that would outlast everything else about 1977. Think about what else was happening in 1977. Star Wars came out, Elvis died, the Apple II computer was released, the Voyager Golden Record was being assembled by a small team led by Carl Sagan. All of that is history now, fading memory. The technology from 1977 is ancient. The politics are barely relevant. The culture has moved on. But Voyager 2 is still operational, still sending data, still representing that moment when humanity reached beyond Earth and said, "We're going farther." The spacecraft will outlast the empires that launched it. The United States as we know it. The Soviet Union already fell. Nations rise and fall. Political systems come and go. But Voyager 2 keeps moving. It'll outlast the species that might replace us. If humanity goes extinct, if something else evolves intelligence on Earth, Voyager 2 will still be out there, still carrying that record, still representing a species that no longer exists. It'll outlast Earth itself. Eventually, 5 billion years from now, the Sun will expand into a red giant. It'll engulf Mercury, Venus, possibly Earth. The planet that built Voyager 2 will be consumed by the star that gave it life. But Voyager 2 will still be out there, drifting through the galaxy, unaffected, indifferent, still carrying the golden record with sounds from a world that no longer exists. That's not speculation, that's physics. The spacecraft is moving fast enough to escape the solar system. The Sun's expansion won't reach it. When our star dies, Voyager 2 will simply continue its journey, now orphaned from the system that created it. This is where the mission stops being about exploration and becomes something else entirely. Philosophy, existentialism, a meditation on what it means to exist in a universe that will continue long after we're gone. Voyager 2 forces us to confront our own impermanence, not just as individuals, not just as a civilization, but as a species, as a planet, as a solar system. Everything ends. That's not pessimistic. That's just reality. Stars die. Planets are consumed. Species go extinct. Civilizations collapse. Nothing lasts forever, except apparently a spacecraft we launched in 1977. The irony is overwhelming. We're so focused on survival, on legacy, on being remembered. And the thing that'll last longest isn't a monument or a book or a piece of art. It's a machine we sent into space to take pictures of Jupiter, and it's not even functioning anymore. By the early 2030s, Voyager 2 will go silent. No more data, no more communication, just a dead spacecraft drifting through the void. But it'll still be there, still moving, still carrying that record, The golden record itself is designed to last billions of years. The protective aluminum cover, the gold-plated copper disc, the carefully etched instructions for how to play it. Scientists have studied how long the record will remain readable. The exterior side, exposed to interstellar dust and radiation, will gradually erode. Tiny impacts from hydrogen atoms and dust grains will wear away the surface. After 5 billion years, the exterior side has about a 20% chance of still being readable. That's Voyager 2. Its twin, Voyager 1, has worse odds. 99% chance the exterior is destroyed. But the protected side, the side facing the spacecraft body, has much better odds. It's shielded from most impacts. It could remain intact for tens of billions of years. Long enough to outlast the Sun. Long enough to witness the Milky Way colliding with Andromeda. Long enough to see galaxies we can currently observe disappear beyond the cosmic horizon. The record contains sounds from Earth, thunder, wind, whales, a mother's first words to her newborn child, music from Beethoven, Chuck Berry, traditional songs from cultures around the world. There are greetings in 55 languages, images of human anatomy, mathematical definitions, scenes from daily life, and all of it is traveling through space on a dead spacecraft that nobody will be able to communicate with. Whoever finds it, if anyone ever does, won't know anything about us except what's on that record. They won't know about wars or politics or the specific reasons Voyager 2 was launched. They'll just know that we existed, that we created music, that we thought about the universe. The record includes a diagram showing Earth's location relative to 14 pulsars. Pulsars are rotating neutron stars that emit regular pulses of radiation. They're like cosmic lighthouses, each with a unique frequency. The diagram shows the direction and frequency of these pulsars from our solar system. It's a map, a way for whoever finds Voyager 2 to figure out where it came from. Except there's a problem. Pulsars slow down over time. The frequencies change. After a few million years, that map won't be accurate anymore. After a few 100 million years, it'll be completely useless. So even our attempt to say, this is where we came from, has an expiration date. Eventually, Voyager 2 won't just be carrying a message from a dead civilization. It'll be carrying a message with no return address. Just a gold-plated disk with sounds and images from a species that once existed somewhere in the galaxy. Good luck figuring out where. And that raises an uncomfortable question. What if nobody ever finds it? What if Voyager 2 drifts through space for billions of years and never encounters another intelligence? That's the most likely scenario, actually. Space is incomprehensibly vast. The distances between stars are enormous. The probability of Voyager 2 actually passing close enough to another star system for someone to detect it is vanishingly small. It's like throwing a message in a bottle into the ocean and hoping it reaches a specific beach on the other side of the world. Except the ocean is 1 trillion times larger and the bottle is moving in a random direction. The spacecraft will pass within about 1.7 light-years of Ross 248 in about 40,000 years. That's not particularly close. That's more than 100,000 times the distance from Earth to the Sun. Nobody's detecting Voyager 2 from 1.7 light-years away. Not unless they're specifically looking for it. Not unless they have technology far beyond what we can currently imagine. So the golden record might never be found, never be played, never be decoded. The message might drift through space forever, without ever reaching anyone. And somehow, that doesn't diminish what we did. If anything, it makes it more meaningful. We sent that message knowing it might never be received. We put sounds and images from Earth on a spacecraft, knowing it might drift through the void for eternity without ever encountering another intelligence. We did it anyway, because the act of sending the message matters. The attempt to communicate across space and time matters, even if nobody ever hears it. That's what Voyager 2 represents. Not the destination, not the scientific data, not even the possibility of contact with alien intelligence. It represents the human impulse to reach out, to say, "We were here," even when nobody's listening, to create something that outlasts us, even knowing it might never serve its intended purpose. We're a species that builds monuments to ourselves, pyramids, cathedrals, statues. We want to be remembered. We want to leave something behind. Voyager 2 is the ultimate monument, not because it's the most impressive thing we've ever built, not because it'll definitely be found, but because it forces us to think about legacy on a scale that dwarfs everything else we've ever done. Every other monument we've built is temporary. The pyramids will erode. The Great Wall will crumble. Mount Rushmore will weather away. Cities will fall. Everything on Earth's surface will eventually be destroyed, either by human action or natural processes, or the sun's eventual expansion. But Voyager 2 is already beyond all of that. It's already escaped. It's already guaranteed to outlast everything else. The spacecraft itself might eventually be destroyed by a collision with something in space. That's possible. Unlikely, but possible. But until that happens, it'll keep drifting. Keep carrying that record. Keep representing humanity long after humanity is gone. And that changes something fundamental about how we see ourselves. We're not just living in the present anymore. We're not just thinking about the next generation or the next century. We're part of a story that stretches across billions of years. A story that started with single-celled organisms and might end with the heat death of the universe. A story where one species, for a brief moment, launched a spacecraft that escaped its own solar system. That's our contribution to the cosmos. Not empires, not wars, not political systems. A spacecraft with a golden record, drifting through space, carrying sounds from a planet that might not exist anymore. The silence that's coming for Voyager 2 is inevitable. The power systems are failing. The instruments are shutting down one by one. Communication will end sometime in the next decade. And then nothing. Just a dead machine in the void. No more data, no more signals, no more connection to Earth. But the spacecraft won't stop moving. It'll keep going. Same trajectory, same speed. Just silent now. An artifact instead of an active mission. That final moment, when the last signal is received, will be one of the strangest in human history. The engineers at NASA will send the final command. They'll wait 19.5 hours for confirmation, and then they'll wait for the last transmission, and then it'll be over. Voyager 2 will transition from an active spacecraft to a historical relic. Still out there, still moving, but no longer ours in any meaningful way. We won't know where it is anymore. We won't be able to track it. It'll just be somewhere in interstellar space, drifting in whatever direction Neptune sent it back in 1989. That's the real destination. Not any particular star, not any specific region of the galaxy. The destination is silence, anonymity, becoming just another piece of debris floating through space. Except it's not debris. It's a message, a monument, a testament to a species that once looked up at the stars and decided to send a piece of itself into the infinite dark. The golden record changes everything about what Voyager 2 means. Without it, the spacecraft would just be a dead probe floating through space. Interesting from an engineering perspective, maybe worth remembering as a historical achievement, but ultimately just another piece of space junk that happened to travel farther than most. The record transforms it into something else entirely. It's a message in a bottle, except the ocean is space, and the bottle might float for billions of years before anyone finds it, if anyone finds it at all. That record contains 116 images, sounds from Earth, music, greetings in 55 languages. It's a snapshot of humanity in 1977, frozen in gold-plated copper, protected by an aluminum cover with instructions etched on the surface. The instructions are fascinating because they assume nothing. They can't use any human language, can't reference any human culture, can't rely on any shared context between us and whoever might find it. Instead, they use universal constants, mathematical relationships, physical properties that should be the same everywhere in the universe. The cover shows the hydrogen atom's hyperfine transition, a reference point for time and scale. It shows the position of our Sun relative to 14 pulsars, cosmic lighthouses with distinctive signatures. It shows how to play the record, how to decode the images, how to interpret what you're seeing. It's the most carefully designed communication ever created because it had to work for an audience we can't imagine, using a context we can't predict, at a time we can't specify, and it might never be found. The odds of Voyager 2 being discovered by another civilization are essentially zero. Space is too big. The spacecraft is too small. Its trajectory doesn't take it close to any known stars for tens of thousands of years, and even those encounters are measured in light years of distance. The record isn't really for aliens, it's for us. It's a mirror that forces us to think about what we'd want to say if we could send one message to the universe. What matters? What should be remembered? What represents humanity at its best? The team that created the record, led by Carl Sagan, wrestled with these questions for months. They had limited space, limited time. They couldn't include everything. They chose sounds of earth, thunder, wind, surf, birds, whale songs, human heartbeat, footsteps, laughter, a mother's first words to her newborn child. They chose music that spanned cultures and centuries. Bach, Beethoven, Chuck Berry, traditional songs from Peru, Zaire, India, Japan, trying to show the breadth of human creativity without privileging any single tradition. They chose images showing science, mathematics, human anatomy, Earth's landscapes, animals, cities, technology, a diagram of DNA, a photograph of a sunset, a woman breastfeeding, a man drinking from a water fountain. Every choice was a compromise. Every inclusion meant something else had to be excluded. How do you represent 7 billion people in 116 images and 90 minutes of sound? You can't. But you try anyway. The record also includes spoken greetings in 55 languages, each one brief, just a few words. Hello from the children of planet Earth in English, peace in Hebrew, greetings to our friends in the stars in Hindi. We wish you longevity in Wu Chinese. These greetings reveal something interesting. Most of them express hope, Friendship, peace, a desire for connection. That wasn't inevitable. Humanity in 1977 was violent, divided, locked in a Cold War that could have ended civilization. The team could have chosen greetings that warned of our capacity for destruction, that acknowledged our flaws, that presented a more realistic picture of who we were. Instead, they chose optimism. They chose to show humanity as we'd like to be seen, as we hope to become. That's what makes the record powerful. It's not just documentation, it's aspiration. The physical record itself will outlast almost everything else humanity has created. The gold plating protects it from erosion. The spacecraft's body shields one side from interstellar dust impacts. Studies have calculated how long the record might remain readable. The exterior-facing side, exposed to space, will gradually degrade. Tiny particles of dust, hitting at 15 kilometers per second, will slowly sandblast the surface over billions of years. After 5 billion years, there's about a 20% chance that exterior side will still be readable. That's actually remarkable. Most human artifacts last thousands of years at best. This one might last billions. The protected side, shielded by the spacecraft, has much better odds. It could potentially remain intact until the Milky Way collides with Andromeda galaxy in 4 or 5 billion years. And if Voyager 2 gets ejected into intergalactic space during that merger, the record might last even longer. Intergalactic space is emptier than interstellar space. Less dust, fewer particles, less erosion. The record could theoretically survive until the end of the universe itself, until the last stars burn out and everything goes dark. That's not guaranteed. The spacecraft could hit something, could get destroyed by an encounter with a rogue planet or a close pass to a star. But if it doesn't, the record might outlast Earth, the Sun, our entire solar system. Think about that. Every human who ever lived, every civilization, every empire, every war, every achievement, all of it will eventually be gone, erased by time. But this record, this 12-inch disc of gold-plated copper, might still be out there, still carrying sounds from a planet that doesn't exist anymore. That creates a strange kind of immortality, not for any individual, not for any nation or culture, but for the species as a whole. As long as that record exists, somewhere in the universe there's evidence that we were here, that we created music, that we looked up at the stars, that we tried to reach out beyond ourselves. It doesn't matter if anyone ever finds it. The act of sending it is what matters, because it means we thought beyond our own survival. We created something meant to outlast us. We sent a message knowing we'd never get a reply. That's fundamentally different from every other monument humanity has built. The pyramids were built to honor pharaohs, the Great Wall to defend territory, Mount Rushmore to celebrate presidents. All of those monuments had immediate purposes. They meant something to the people who built them. They served contemporary goals. The golden record serves no contemporary purpose. It won't be found for tens of thousands of years at minimum, possibly millions of years, possibly never. It exists purely as a statement. We were here. We existed. This is what we valued. And the fact that we sent it, that we spent time and resources creating it, says something profound about human nature. We want to be remembered, even if there's no one left to do the remembering. Even if the universe itself might end before anyone finds what we left behind. We still want to leave a mark, still want to say we mattered. still want to believe our existence meant something beyond our brief moment in cosmic time. The Golden Record is the ultimate expression of that impulse. It's humanity's message to eternity, carried on a spacecraft that will drift through space long after everything else we've built has turned to dust. But here's what nobody talks about when they discuss the record. The real message isn't what's on it. The real message is that we sent it at all. Any civilization advanced enough to find Voyager 2 and play the record will already know everything important about us. They'll know we achieved spaceflight. They'll know we understood physics and mathematics well enough to navigate the solar system and escape it. They'll know we thought beyond ourselves, that we imagined other civilizations, that we tried to communicate across the void. That tells them more about humanity than any photograph or sound recording ever could. It tells them we were curious, hopeful, creative, that we reached toward the unknown even when the reaching seemed pointless. The content of the record is almost beside the point. It's the fact of the record that matters, the decision to send it, the effort to create it, the hope it represents. And that hope is still traveling through space right now, silent, alone, moving at 15 kilometers per second toward nowhere in particular. It'll keep moving through the Oort Cloud, past the first stellar encounters, through the local bubble and beyond, through regions of the galaxy we can't even imagine yet. And everywhere it goes, it carries this message. We existed. We looked up. We tried. That might not seem like much, but it's everything. Because in a universe that's mostly empty, mostly dark, mostly silent, creating something that says, "We were here," is an act of defiance, a rejection of cosmic indifference, a statement that existence matters even if the universe doesn't care. The Golden Record is humanity's way of saying we refuse to disappear without a trace. We refuse to accept that our brief moment of consciousness in an ancient universe means nothing. We choose to believe it means something. And we're sending proof of that belief into the infinite dark. Whether anyone ever finds it doesn't change what it represents. The sending is the point. The trying is the point. And that makes Voyager 2 more than a scientific mission, more than an engineering achievement, more than a historical artifact. It makes it a testament to what it means to be human, to exist in a universe we barely understand, to know we're temporary, to choose hope anyway. And that journey is almost over in one sense, just beginning in another. Because while the hope will travel forever, the mission won't. Voyager 2 is dying, not dramatically, not catastrophically, just slowly winding down in exactly the way you'd expect something to, after nearly 50 years of continuous operation in the most hostile environment imaginable. The spacecraft is powered by 3 radioisotope thermoelectric generators, nuclear batteries that convert heat from decaying plutonium-238 into electricity. At launch in 1977, they produced 470 watts of power, enough to run several scientific instruments, the communications system, the attitude control thrusters, and all the other systems needed to keep a spacecraft functioning. Now they produce less than half that, and the number drops by about 4 watts every year as the plutonium continues its steady radioactive decay. This decline has forced NASA engineers to make increasingly difficult choices about which systems to keep running and which to shut down forever. Each decision represents a trade-off between competing priorities. Which instruments still provide valuable data? which consume the most power, which can tolerate operating at temperatures far below what they were designed for. In October 2024, they shut down the Plasma Science instrument, the same instrument that definitively proved Voyager 2 had crossed into interstellar space. The instrument that provided data no other spacecraft could obtain because Voyager 1's plasma detector failed back in 1980. That hurt, but it bought time for the remaining instruments. Then in March 2025, the low-energy charged particle instrument went dark. Another piece of history switched off to preserve what little power remained. Soon the cosmic ray subsystem will follow. Mission planners expect that shutdown to happen sometime in 2026, leaving just 3 instruments operational. The magnetometer will keep measuring the interstellar magnetic field. The plasma wave subsystem will continue detecting oscillations in the sparse plasma that fills the space between stars. And one other instrument will hang on for as long as the power holds out. Current projections suggest the spacecraft might maintain operation with a single instrument into the early 2030s. Maybe 2032, possibly 2033 if everything goes perfectly and no unexpected failures occur. Then silence, complete and permanent. The spacecraft will continue transmitting its carrier signal for a brief period after the last instrument shuts down, a wordless tone that simply says, "I'm still here." But eventually, even that will fade, as the remaining power becomes insufficient to drive the transmitter. And at that point, somewhere around the mid-2030s, humanity's conversation with Voyager 2 will end. The last command will be sent, the last confirmation received, the last data point transmitted across the void. The Deep Space Network antenna in Canberra, Australia, the only antenna in the southern hemisphere capable of communicating with the spacecraft, will point toward empty space and hear nothing. But the spacecraft won't stop. It'll keep moving at 15 kilometers per second, keep tumbling slowly through the interstellar medium, keep carrying the golden record deeper into the galaxy. Just silently now, for the next 300 years, Voyager 2 will travel through the space between the solar system and the Oort Cloud, that vast theoretical shell of icy objects that marks the true boundary of the Sun's gravitational dominance. The density of matter in this region is so low, it makes the best laboratory vacuum look crowded. A few atoms per cubic centimeter, nothing more. Around the year 2326, the spacecraft will reach the inner edge of the Oort Cloud and begin its 30,000-year transit through this region. Think about that timeline for a moment. 30,000 years. The entire span of human civilization, from the first agricultural settlements to the present day, is only about 12,000 years. Voyager 2 will spend more than twice that long just passing through the Oort Cloud. And during that entire time, it'll be completely inert. A piece of metal and plastic and gold drifting through darkness. Dead in every functional sense, but still moving according to the laws of physics that have governed its motion since Neptune's gravity sent it on this trajectory in 1989. The chances of it hitting anything are essentially zero. The Oort Cloud may contain billions of icy objects, but they're separated by such vast distances that the spacecraft could pass through the entire region without coming within millions of kilometers of a single comet. Around the year 61,000, Voyager 2 will emerge from the Oort Cloud's outer edge, and at that point, for the first time, it will truly have left the solar system. The sun's gravity will still affect it. You can't ever completely escape a gravitational field. But other stars will pull harder. The spacecraft will have become an interstellar object, no longer bound primarily to the star it left behind. Its trajectory from that point forward will be determined by the complex gravitational interplay of multiple stars, the overall galactic field, and random encounters with molecular clouds and dust. In about 40,000 years, Voyager 2 will pass within 1.7 light-years of Ross 248, a small red dwarf star in what we currently call the constellation Andromeda. This will mark the first time the spacecraft has been closer to another star than to the Sun. The year will be approximately 41,977 CE. Human civilization, if it still exists, will be unrecognizable. The languages on the Golden Record will be ancient history. The very concept of nation-states that built the spacecraft will seem as alien to future humans as Neolithic tribal structures seem to us. But Voyager 2 will pass Ross 248 exactly as physics demands. Silent, unchanged, except for the gradual erosion of its surface from impacts with individual atoms of hydrogen over millennia. The journey continues. In the year 298,000, it'll swing within 4 light-years of Sirius, the brightest star in Earth's sky. Then around the year 400,000, it'll pass near Delta Pavonis and GJ 754. These aren't close encounters. Light-years of distance separate the spacecraft from each star, but they're milestones, markers along an infinite road. And all the while, the Golden Record keeps traveling, protected on one side by the spacecraft body itself, exposed to space on the other. Research suggests the exposed side will gradually erode. Impacts from interstellar dust particles and atoms will slowly wear away the grooves containing the encoded images and sounds. After 5 billion years of this erosion, the exposed side will likely be unreadable. But the protected side should survive far longer. Possibly until the Milky Way itself merges with the Andromeda galaxy in about 5 billion years. Maybe even beyond that if the spacecraft gets ejected into intergalactic space during the merger, where erosion rates would drop to almost nothing. 5 billion years. That's longer than Earth has existed, longer than life has persisted on this planet. Longer than our sun will continue burning before it swells into a red giant and consumes the inner planets. And through all of that deep time, the Golden Record will carry its message. Not because it's likely to be found. The probability of another civilization encountering Voyager 2 in the vastness of space is effectively 0. But because we sent it anyway. That's what makes this mission transcendent. Not the science it accomplished, though that was historic. Not the engineering achievement, though that was remarkable. Not even the length of the journey. It's the fact that we chose to send a message knowing it would almost certainly never be received. We built something to last billions of years, knowing our entire civilization might not last thousands. We reached toward the unknown with full awareness that the reaching was probably futile. And we did it because the alternative, sending the spacecraft without the record, seemed wrong. Seemed like a missed opportunity to say something about who we are and what we value. Every civilization that has ever existed has tried to leave something behind. Monuments, art, writing, records of their existence carved in stone or preserved in libraries. Voyager 2 is humanity's monument to deep time, our attempt to leave a mark that outlasts everything else we've built. A statement that we existed, we thought, we felt, we created, we wondered about the cosmos and our place in it. That impulse, to matter beyond our moment, might be the most human thing there is. And now that impulse is encoded on a golden disk, moving at 15 kilometers per second toward a future so distant, we can't begin to imagine what it'll look like. The spacecraft will keep going long after the sun has died, long after Earth has been consumed, long after every trace of human civilization has vanished from the cosmos. It'll drift through stellar neighborhoods we'll never see, past stars that haven't been born yet, through regions of the galaxy that are currently just diffuse clouds of gas and dust. It'll witness the evolution of the Milky Way from a perspective no conscious being may ever share. And somewhere in all that deep time and vast distance, it'll carry proof that once, on a small blue planet orbiting an unremarkable star, something existed that could think and create and hope and send pieces of itself toward the infinite dark. That's Voyager 2's final destination. Not a place, not a star system, not a specific endpoint. Its destination is eternity itself, the endless future, the vast sweep of cosmic time that makes all human timescales seem like single heartbeats. And in choosing that destination, in sending this spacecraft on a journey that has no end, we made a choice about what matters. We chose to believe that existence is worth celebrating, even if the celebration outlasts the celebrants. That consciousness deserves to be documented, even if the documentation survives longer than the consciousness itself. That the brief moment when matter organized itself into beings capable of wonder is worth preserving for a universe that may never care. We chose hope over nihilism, meaning over meaninglessness, the symbolic gesture over practical silence. And that choice is still moving through space right now, frozen in metal and gold, encoded in grooves on a record, expressed in the simple fact of a machine that refuses to be forgotten. Voyager 2 will never stop unless something stops it, and in the almost empty space between stars, nothing will. So it'll just keep going, through the Oort Cloud, past Ross 248, beyond Sirius, through the local bubble, into whatever comes after, carrying humanity's message to no one in particular and everyone in general. A time capsule from a species that existed for a cosmological instant, but tried to matter for eternity. That's what makes this more than a space mission. It's philosophy in motion, a statement about existence expressed through engineering, a question posed to the universe that we'll never hear answered. And maybe that's exactly as it should be, because the value isn't in the answer, it's in the asking, the reaching, the trying. The golden record will keep spinning through the dark, and wherever it goes, it carries this truth. We were here, we looked up, and we refused to let our moment pass without leaving something behind. The final instrument will shut down sometime in the early 2030s. The exact date isn't certain. Could be 2032. Could be 2033. Depends on how efficiently the remaining power can be managed and whether any unexpected failures accelerate the timeline. When it happens, there won't be any ceremony, no countdown, no final speech from mission control. Just engineers in a room somewhere, sending the last command sequence across 20 billion kilometers of empty space, waiting 39 hours for confirmation, and then watching the signal fade to nothing. That silence will spread outward from the spacecraft like a wave. First, the Deep Space Network antenna in Canberra will lose contact. Then the tracking stations will remove Voyager 2 from their schedules. Then the mission operations team will disband. Then the engineers who spent decades managing the spacecraft will retire or move to other projects. Within a generation, nobody working at NASA will have direct experience with operational Voyager missions. It'll become history, something that happened, something we did once. But the spacecraft won't care about any of that. It'll keep moving at 15 kilometers per second whether we're listening or not. The laws of physics don't require an audience. 3 centuries from now, around the year 2326, Voyager 2 will reach the inner edge of the Oort Cloud. The spacecraft will be roughly 1,000 astronomical units from the Sun, about 30 times farther than it is right now, and it'll still have 99,000 more astronomical units to cross before it emerges from the far side. The Oort Cloud is where our solar system truly ends, not at the heliopause where the solar wind gives way to interstellar plasma, not at Neptune's orbit or Pluto's or the Kuiper belt. The Oort Cloud is the boundary of the Sun's gravitational dominance. Everything inside it belongs to our star. Everything beyond it belongs to the galaxy. Voyager 2 will spend 30,000 years crossing that boundary, longer than recorded human history, longer than agriculture has existed, longer than we've had cities or writing or mathematics, or any of the tools we used to build the spacecraft in the first place. And during that entire crossing, it'll be dead. Silent, just mass and momentum, physics in its purest form. Around the year 61,326, Voyager 2 will emerge from the Oort Cloud's far edge. At that moment, it will truly leave the solar system. The Sun's gravity will still affect it. You never completely escape a gravitational field, but other stars will pull harder. The spacecraft will belong to interstellar space in every meaningful sense. What happens after that is harder to predict with precision. The gravitational landscape becomes too complex, too many variables, too many stars pulling in different directions. We know the spacecraft will pass within about 1.7 light-years of Ross 248 in roughly 40,000 years. That's the first stellar encounter, the moment when Voyager 2 becomes closer to another star than to the one that launched it. After Ross 248 comes Sirius, about 300,000 years from now. Then Delta Pavonis and GJ 754, around 400,000 years out. Each encounter distant, each measured in light years rather than astronomical units. The spacecraft won't be captured by any of these stars, won't enter orbit, won't even be significantly deflected, just gliding past at a distance, continuing its journey. 5 to 6 million years from now, Voyager 2 will exit the local bubble, that region of low-density gas carved out by ancient supernova explosions. Beyond that, the trajectory becomes increasingly uncertain. Molecular clouds could slow it down slightly. Close passes to stars could alter its course. Encounters with rogue planets could redirect it entirely. Over billions of years, these small perturbations accumulate. The spacecraft's path becomes essentially unpredictable. We can say it'll be somewhere in the galaxy, still orbiting the galactic center along with hundreds of billions of stars. But where exactly? The uncertainty grows larger than the distance between stellar systems. 4 to 5 billion years from now, the Milky Way will collide with Andromeda. Computer simulations suggest Voyager 2 has about a 50% chance of being ejected from the merged galaxy entirely during this event. If that happens, the spacecraft will find itself in intergalactic space, the void between galaxies, crossing distances measured not in light years, but in millions of light years. In that environment, erosion essentially stops. The density of matter in intergalactic space is so low that atomic impacts become rare events. The golden record could remain readable for trillions of years, long after the sun has burned out, long after Earth has been consumed, long after the last stars in the merged galaxy begin to fade. But even if Voyager 2 remains in the galaxy, even if it spends the next trillion years orbiting the galactic center, the record will survive for deep time. The protected side, shielded by the spacecraft body, could persist until proton decay becomes relevant, until the fundamental particles that make up matter begin to fall apart. That's a timescale so vast, it makes billions of years look brief, 10 to the 34th years or more. Numbers that lose meaning. Durations longer than the current age of the universe multiplied by trillions. And through all of that incomprehensible time, the spacecraft will carry its message. Not because anyone is likely to find it. The probability of another civilization encountering Voyager 2 is effectively zero. Space is too vast, the spacecraft too small, the odds too long, but because we sent it anyway. That decision, made in 1977 by people who knew the message would almost certainly never be received, reveals something essential about what it means to be human. We create meaning even when the universe doesn't demand it. We build monuments to ideas rather than to practical purposes. We reach toward impossible goals because the reaching itself matters. The golden record won't save humanity, won't preserve our civilization, won't guarantee we're remembered. It's not a backup plan or an insurance policy or a practical investment in the future. It's a statement, an expression of hope, a rejection of the idea that our brief existence in cosmic time is meaningless. Every sound on that record, every image, every greeting in 55 languages, every note of music from Bach to Chuck Berry represents a choice to believe that consciousness matters, that beauty matters, that the strange fact of the universe becoming aware of itself through evolved beings on a small planet is worth documenting. The spacecraft carries proof that we existed, but more than that, it carries proof that we cared about existing, that we thought about our place in the cosmos, that we tried to communicate across the void, even knowing the communication would probably never reach anyone. That's what outlasts us, not our buildings or our wars or our political systems, not our technology or our wealth or our temporary certainties about how the world works. What outlasts us is the simple fact that we looked up at the stars and wondered, that we built something designed to survive billions of years purely to say we were here. Voyager 2 is humanity's message to deep time, to the vast future, to whatever might come after us in the cosmic story. And that message is still traveling right now. Silent, alone, moving at 15 kilometers per second through absolute darkness toward a destination it will never reach because it has no destination. Just an eternal trajectory through space and time. The mission ends in the early 2030s when the last instrument shuts down and the final transmission fades to silence. But the journey never ends, can't end. The spacecraft will keep moving as long as physics allows, which is essentially forever. That's the final place Voyager 2 will reach before it dies. Except it won't die. Not really. It'll just stop talking, stop transmitting, stop being part of our world, but it'll keep being part of the universe, keep carrying the golden record, keep representing a moment when one species on one planet chose to send a piece of itself into the infinite dark. And in choosing to send that message, knowing it would outlast everything else we've ever built, we made a statement about what we value, about who we are, about what we hope existence means. The spacecraft will drift through the Oort Cloud while human civilization transforms beyond recognition. It'll pass Ross 248 while species rise and fall on Earth. It'll witness the Milky Way-Andromeda merger while our sun becomes a white dwarf cooling in the galactic dark. And everywhere it goes, it carries this truth. Consciousness happened. Intelligence emerged. Beings capable of wonder existed briefly in the universe, and they tried to leave something behind. That's not everything, but it's something. And in a universe that's mostly empty, mostly dark, mostly silent, something is enough. The final destination isn't a place. It's a state of being, eternal motion through cosmic time, perpetual witness to the universe's evolution, a monument to curiosity that outlasts the curious. Voyager 2 will keep going long after the last person who remembers its launch has died, long after the last person who knows what a spacecraft is has disappeared, long after humanity itself becomes unrecognizable or vanishes entirely. It'll just keep moving, carrying sounds from a world that no longer exists, images from a species that came and went, music composed by beings who briefly achieved consciousness and chose to create beauty. And that's exactly what we intended when we launched it. We knew it would outlast us. We built it to outlast us. We sent it on a journey with no return because the journey itself was the point, not the destination, not the discovery, not the practical benefit. The journey, the attempt, the reaching towards something larger than ourselves. That's what Voyager 2 represents in the end. The human impulse to matter, to leave a mark, to refuse to disappear without trace. We existed, we looked up, we wondered, we tried, and somewhere in the dark between stars, that truth is still traveling.